Hey, hello, Physics 110 students. You just got done with exam one. I thought I would make a solution this morning and start the grading. Also, this gives you a good chance to kind of self-grade. I like this idea that I put a video, I put it out there. Number one, I think you're kind of very interested in how you do, so I think you'll kind of pay close attention to this video. And then number two, if you made any mistakes, I think it's still fresh in your mind and you'll be able to correct that. So it's a great learning process. And of course, along the way, you can, kind of grade yourself. It's easy on the multiple choice. It's a little bit hard to on the free response to grade yourself, but you'll have some idea of what points you got here. So let me just run through this, and you can see what you did right and what you did wrong, and hopefully improve. Don't beat yourself up. This first exam is always a little bit of challenging for people. I think learning to think in terms of physics takes a little training, and you'll get better at it with each passing week. And by the time the whole year's over, by the time you're, next May, I think you'll, kind of forget about how difficult this was getting started. But let's just run through this. I'll go through the multiple choice. Here it says a league. If you're not familiar with the league, it's 3 miles, kind of an old unit. So how many miles would there be in 20,000 leagues under the sea? So it's a unit conversion, and of course you might start with 20,000 leagues. And then this is our unit conversion. We want to get rid of leagues and turn it into miles, and the conversion is 3 to 1. And so that makes 60,000. And so D would be the answer to question number 1. Now, question number 2 here says a bike is traveling with this speed. The rider applies the brakes for about 3.5 seconds, slowing the bike at this rate. What is the new speed of the bike? And then hopefully you're looking at this equation, which gives you initial speed, final speed, acceleration, all that good stuff. And again, we have those kinematic equations. And so it works for constant acceleration. So here it is. And so I guess I would be starting with, let's see, a bike is traveling with a speed of 11.2. Bike applies the brakes, and so minus 1.25 for 3.5 seconds. And so this should be 11.2 minus 1.25 times 3.5, and this should be around a 6.63, and so that should be answer C. Okay, awesome. Let's see. Go to the next page here. What should I do with that page? All right, number 3. A model rocket starting from rest at a height of 0 is launched vertically upward with an acceleration of. The rocket reaches a speed of before the engine stops. How high is the rocket when the engine stops? Okay, so we know the acceleration and we know the speed both before and after, and it asks for distance. And we have those 5 kinematic equations, and the one that is missing time, as I like to phrase, is this one. And so that's the one that pops into my head first, because this problem describes some constant acceleration without time in it. And so we're not asked to solve for time, and so that's why this is a good equation to use. No, because we don't have time in it. We're not asked to solve for it, and we don't need it to punch into our equation. So in this case, I guess the initial speed would be 0. So rocket starts from rest at a height of 0. And then it goes until it is at 21.7, and I'll square that. 2 times the acceleration, which is 12.2, and then we can solve for how high it goes, or how much it increases, and of course starting at 0. So this side of the equation would be the 21.7 squared. I could then move the 2 to the other side and underneath. And I could also move the 12.2 to the other side and underneath, and coming up with about a 19.3. So it looks like B would be the correct answer for number 3. Now, number 4 is a continuation of this. And so let's see if I can kind of leave work we did in number 3 and also kind of talk about number 4. Because number 4 might be the hardest one of these multiple choices, because it says using the same information as number 3 and repeated below, just in case you wanted to see some of the numbers and focus on it. How much time elapsed, and this is important, from launch to maximum height. And here's where I think the problem can get a little harder than the other ones. Is we have what is described in number 3 as the rocket going up, and we just said it went to a height of 19.3. And then the engine cuts off, and so at this point, as the problem says, it's heading upward at 21.7 meters per second. So once the engine cuts off, it's still going to go upward. Of course, now it slows down because gravity slows it down, so it's going to go up an additional height and an additional amount of time. And let me go back to the question. I'm trying to remember now if it asked the total height or the total time. But my point here is you would have to put the two together. So if they ask for the total height, I need to take this 19.3 and add it to this additional more height. If they ask for time, I guess I need to get the time for the first leg and time for the second leg and add those together. And so what did it say here? How much time elapses? Okay, so why don't I, over here, put how much time elapses for each exercise, and over here, how much distance. And I'm probably just wasting my time doing distance, but since I'm not taking a timed exam, I'll go ahead and do that for you. But you could do this second part here like we did the first part, where you can put in final speed squared, initial speed squared, 2 times acceleration, and get a delta x. Because in this case, from here up to here, the final speed would be 0. The initial speed would be the 21.7, so I'll square that. The acceleration is now the negative 9.8, and then we get our delta x. And so this calculation, which, as I said, is really unnecessary, would tell us that additional height. And so 21.7 squared, maybe I'll just hit enter. And thinking of it on that side would now make it a negative. But then I'm going to divide by a negative. So I'll just kind of ignore the negative and just divide by a 2 and divide by the 9.8 with the negative already canceled off. And so this is going to go up 24.0 more. And again, like I said, I'm kind of just wasting my time here because we don't ask for that height or the total height, so it's not really needed here. But it does make me feel pretty good about the number because I know that going up, it had an acceleration greater than 9.8. And so to get up to this speed took a certain amount of distance, and I would think since it's going to be slowing down at 9.8, which is smaller than what it was speeding up, that it would need more distance. And sure enough, it does by a little bit more, 24 meters versus the 19.3. So the numbers make sense in terms of kind of interpreting how big they are. But let's come over here and focus our attention then on the time, and then we could use then equation number 1 for that. And so on the way up, the final speed is the 21.7, the initial is 0, the acceleration is 12.2, and then from that we can get the time. And so 21.7 divided by 12.2 gives me about a 1.78 seconds on the first part of it. And I guess that kind of, if that's what they asked, how much time before the rocket gave out, then, A would be the correct answer there. But if we apply that same logic here to the second half, where the engine cuts out, this would be 0. The initial speed during this second half where the engine cut out is that 21.7. The acceleration is at negative 9.8, and then we can solve for time during the second part of this. So 21.7. When I move it to that side, it's negative and also divide by a negative. So I'll just ignore the two negatives. And it looks like I get a 2.21 for the second part of it, which I guess is the answer for C. But the correct answer would be then the total time of these two. So 2.21 for the second part of the motion, and the 1.78 for the first part of the motion is 3.99, or I guess, other than some rounding here, it would be 4 seconds. And so I'm going to put here 4 seconds for the answer. So that pen is getting a little dry. Let me switch here. So there's, like I said, I think maybe the hardest one of the multiple choice. All right, so let's try number 5 here. Number 5 says, during a game, a soccer ball is kicked with this speed, okay, and an upward angle here on a level field. How much time elapses between the kick of the soccer ball and it hitting the ground? Well, there's a couple ways to do this one. I'll draw a picture. One thing we did learn in class was the time to get to its highest point and the time to get to its lowest point are the same. So we could calculate the time to the highest point and then double it. On the other hand, we learned about, and that would involve velocities, because I know the vertical velocity is 0 here. Maybe I'll do it not that way. Maybe I'll do it with the equation of position, because what's nice about this one is it directly connects to a description where it leaves at a height of 0 and returns to the same height. In fact, you could call the ground any height you want, since we're going to cancel off, whether you call them both 0 or both 10 meters or something. Now, the bad thing about this equation, though, is it is a quadratic equation. And that's why I was kind of thinking, maybe I'll do velocity so I don't have to deal with the quadratic and all the math there. But once I put in 0, it actually factors out, so it's not really a quadratic at that point. So I'm going to get this, which would be the same thing as if I did velocity. So ultimately, I guess it boils down to the same math. And this is why I factored it, because it equals 0. And so I'll just put it right here. And And just kind of remind yourself of any math that, when you have two things multiplied together and they equal 0, either the first one has to be 0, so either time equals 0, which notice that makes total sense. That time equals to 0 would be right here, and it would be at a height of 0. And so this math is solving for all the moments in time when it's at a height of 0. And yes, at 0 time, it's at 0 height. But that's not the one we want. We want then the second solution, which would correspond to a time when it is, again, also at a height of 0. And this is as it returns back to the ground. So that means the initial velocity in the y plus 1/2 acceleration times time would equal 0. So in this case, I'll put in my initial height, but we got to be careful. This is the initial height in the y direction. So this would be the 13.6 multiplied by the sine of 25 degrees. And the acceleration would be the negative 9.8 and then the t. And let me just check the mode of my calculator that I'm in degrees, okay? Because if I take this 13.6 and then multiply by the sine of 25, I'm going to get an initial upward speed of 5.75. And this would be then a minus 4.9. But if it'll be okay with you, I'll just do this in one step. I'll take the 4.9 and the minus and move it to the other side. And so now I can get the time by dividing that last answer by 4.9. And I get about a 1.17. So it looks like the answer would be B there for question number 5. Okay. So for question 6, here it says a ball rolls off a flat, level roof, and it has this height. The ball hits the ground this far from the building. What is the speed? So I guess if this is the top of the building, it kind of does this. And one thing nice is we know that the speed in the x direction doesn't change. And so if we, did something like x equals x naught plus initial velocity in the x times time, and of course I'll throw this in at the beginning, but using the edge of the table as position 0, and recognizing that it's going to travel, that would be over here, 3.13 meters, and that it's a projectile, so it has no acceleration in the x direction. I have what you might call the beginning steps of our two-dimensional motion. And I'd like to find that. That's what the question is. With what speed did the ball roll off the roof? Okay, so we're trying to find the speed as it rolls off the roof. And to do that, we need time. And so this is our horizontal motion. And I think you guys heard me say many times here in the solutions that when I do these two-dimensional ones, it kind of helps my thought process to have a set of columns, one that's calculating things in the x and one that's calculating things in the y. And so let me apply that same equation in the y. And I always have a decision on these. Do I call down a positive number or a negative number? Traditionally in my math class, I always call down negative. So I kind of want to stick to that. But what's also nice is everything goes in the vertical direction. There's no up and then a down like earlier on. So there would be advantage of calling down positive because then I only have to deal with positive numbers. But maybe I won't do that. Maybe I'll just say, look, it goes down, and there it is. It falls down. So that's going to be a 3.22. And so the final position down is a negative 3.22. whereas the initial is going to be my 0. And then, of course, since it says it rolls off a flat roof and it just goes straight across, there is no upward or downward velocity. It'd be a harder problem if it did. And, of course, we'll see one of those coming up in the free response. But this one is not nearly as hard as the free response one. So the initial velocity there is 0. And then this would be the 1/2, and the acceleration would be the negative 9.8. And so here is my equation that will allow me to solve for time and then use it over here in this column and get the initial velocity. So taking the 1/2 and the negative 9.8, I get a negative 4.9, canceling off the two negatives. I could go 3.22 and divide by the 4.9 when I bring it over. And that technically would be times squared. So let me also take the square root of that. And we're looking at a 0.811. And putting that into here. And then moving it to the other side is going to give me that initial velocity in the x direction. And for that matter, it's the final velocity in the x direction because it doesn't change. 3.13 divided by my last answer. And I get a speed of 3.86 meters per second. And that looks like it would match C. So number 6 is C for the correct answer. Okay. Coming over here to number 7. No numbers, just concepts here. It says a falling object will reach its terminal speed. So we have this falling object, and its terminal speed is, of course, being pulled down, if I did a free body diagram, by its weight. And then there'll be some air resistance. Why don't I just put a capital R for resistance? But Newton's second law says the sum of all the forces equal mass times acceleration. So only when the forces add up to 0 do we get 0 acceleration. And so that would, of course, happen when these are equal and opposite. So I guess that would sound like this one here. The force of air resistance right here is equal to its weight. So its weight's pulling it down, air resistance pulling it up. That gives me a net force of 0. What was this one? The force of air resistance exceeds the weight. No, then it would have an upward more than its weight, and it would be slowing down. Which if you just dropped something, that couldn't happen. But you could give it an initial downward speed greater than its terminal velocity. And then that would slow down until it went to its terminal velocity. That'd be an interesting dynamics there. Okay, well, maybe I better move on to number 8 here. And so number 8 says that we have a 58 kilogram person and is being accelerated upward in an elevator. Okay, so I kind of think of this person in the elevator, and acceleration is being pushed up. So we kind of have something like this, where the upward force has to be greater than the person's weight for that to work. In fact, the free body diagram would look a lot like this last one, where we've got weight pulling down, and then the elevator lifting up. Now, I guess if I put the floor of the elevator, that's where the contact would be made. That's where how the elevator would push up on this person. This elevator floor would be made out of some kind of structurally strong material so it could push up. So I'll just call it up with an upward force. And then, again, using the sum of the forces equals ma, we could say, okay, we have an upward force of F and a downward force of mg, and that must equal to ma. And so that's the free body diagram. And so it says if the upward acceleration is, what is the upward twice, force from the elevator on the person? And so F then becomes the MA, but it also gets an MG. And maybe I'll calculate these each separately because it is a very common mistake to only do the MA. And so I'm not sure how many of you might have done that, but 58 times 1.12 is about a 65.0. And if that's all you did, you might grab A as the answer, but that's just what the net force is. And so if the question had asked for the net force, you would say, well, net force is just MA. But it asked for this individual force. And so this individual force needs to be greater than the weight by MA. And like the one we just did, if the upward force was just equal to weight, the net force would be 0 and you'd have no acceleration. So the other factor here, the 58 times 9.8, the 568.4, which I guess would round to 69. I might, make you pick that one. But it's actually both of these together for the net force of 633.4, which I guess would make answer D the correct one. Well, there's the upward force, not to confuse with the net force. Here is probably our hardest section. This is the terminal one, but a baseball, which is a sphere and it gives you the diameter and the mass, is dropped from a very tall building. What is it? Terminal speed. All right, so here's the ball. Actually, I guess I should have made it round. It's a ball. And it would be pulled down with mg, and of course would have some kind of resistive force. And if it's at its terminal speed, its resistive force must equal the weight going down, because again, some of the forces have to equal ma, and so you're saying it's at its terminal speed, meaning it doesn't accelerate. And so the free body diagram looks like this, with r going up and mg going down, and they have to equal 0 for zero acceleration, because zero acceleration is because we're not changing its speed. We're at a terminal speed. And so that's where this r equals mg comes from. And so in that sense, it's the same idea of what we did in question 7. But here's where we have to kind of grab the textbook and remind ourselves that 1/2 times the drag coefficient times the area times the speed squared is what is equal to the resistive force. And so notice then it depends upon its speed. That's why I kind of made a comment earlier that if to get a resistive force greater than the mg, you've got to be greater than its terminal speed. Because at its terminal speed, they're equal. In fact, you can even put like a little t there to say, okay, this is its terminal speed. And so that's this idea. When all of this force, and so going at its terminal speed, and all those together make a resistance of this much. Okay? So we got a little bit of work here to kind of get the terminal speed. And the first thing we have to do is to look in our book and get the drag coefficient for a sphere. And so we'll flip through the pages, all right, and find this 0.45. And then we got to get the area of it. and they give us the diameter. Now, maybe I'll just remind you the cross-sectional area of a circle is pi r squared. So let me take this diameter and convert it into meters, and let me divide it by 2. All right, so there's the diameter. Convert it into meters, so millimeter, move it out, 3 decimals. Divide it by 2 and square that. So that would be the area, terminal speed squared. And then let me take the mass and also convert that into kilograms. And so there is some unit conversion going on in here. And so this is a pretty tough one too. What one did I say was the hardest? Yeah, number 6, huh? No. It was a continuation here. Remember this one? Yeah. This one's maybe not quite as hard, but it's close. Anyways, and so then I can get terminal speed. And since there's a lot of math here, maybe I better not try to do it all in one shot on my calculator. Maybe I'll just do everything on this side. So this right here, the 0.075 divided by 2, I'll do that first and then square it. Then I'll multiply by a pi. Then I'll multiply by the coefficient of drag for a sphere. And then I will multiply by 1/2, and I'll just enter it as 0.5 on my calculator. And so this side of the equation is 9.94 times 10 to the minus 4. And over here, a little easier calculation is 1.421. So now that I have that 1.421, I can divide by, so I'll just hit divide, and I'll just go over and copy and paste that number. And of course, that's the terminal speed squared. So then I've got a little bit of math to do the square root, and it looks like a 37.8 would then be the terminal speed. And I don't know, maybe that is the hardest. Definitely the material from chapter 5 here with resistance, and both of these 9 and 10 have the resistance. So maybe these are the harder one. Yeah, maybe I'll call that one the hardest of the multiple choice. Because again, it's this terminal stuff. But on the other hand, this is just kind of a direct copy of what was done for you in the book and what on the homework. So in some sense, that's, hopefully not a surprise one at all. And the same thing can be said about here, because we did frictional forces, not just with the terminal speed, but also with the coefficient of friction. And so here, as we take a skier going down the incline, we are going to be heading down at a 38 degrees. And on this one, you might want to just directly look in the book here while you're taking the test, because this one was actually done, and I was trying to remember if it had friction in there or not. I think it did. And so we can kind of do that same thing, that if we do the free body diagram here, and I'll just take the person and put it right there, we can have this mg pulling down, normal force perpendicular to the surface, and then the friction as the person skis down this incline of 38 degrees. And so what we saw many times in the homework is that if we kind of think about down the incline as the x-axis here, okay, then, and I'll just kind of take this force of gravity and think of it as two components. So there's my right angle, where this part is down the hill, and, oh, I didn't give myself kind of enough room to do a split of x and y, what I usually like to do. So let me do that on a clean piece of paper here. But in terms of x, this part would be down the hill. And so it's opposite of this 38 degrees. So down the hill would be mg sine of 38 degrees. And then up the hill would be the force of friction, and that would equal to ma. Whereas in the y direction, we would have the force of gravity, or a component, going in and the normal force going up. So calling this the y direction, I would have normal force going up, and I would have minus mg cosine of 38 degrees. And I guess technically you might say ma, but this a would be the acceleration in the y direction, and as we tilt it, you know, we're going along the x direction. We're not going along the y direction. And so that's going to be a 0. And so that gives us a normal force of mg cosine of 38. And so now we can put these together, because in the x direction, this is an mg sine of 38. And for this type of friction, what we call solid-to-solid friction, so we have the skis on the snow, we're going to have then a minus the coefficient times the normal. And so that's where that normal comes into play. So this becomes mg sine of 38 degrees minus coefficient, and the normal would be mg cosine of 38 degrees equals ma. And so there's quite a bit in this problem too, but one of the first things that pops out is that everything has an m in it. So we can divide everything by m and it goes away, which is really good because they just said a skier heads downhill and they don't say, you know, what the mass is. So this becomes the g sine of 38 degrees minus, and this coefficient of friction then is kind of worth looking up here. And so kind of the same section and pages that we did the cross section. I think this was actually right before it. So this was the section before the drag. Then we can look at the waxed skis on the wet snow. And so now we can put in our numbers. So grabbing my calculator, this first one here would be 9.8 times the sine of 38. Then we could subtract the 0.1 times a 9.8 times a cosine of 38 and get a acceleration of 5.26. And that looks like it's right here for A. All right, well, those I hope went well for you. They can be involved a little bit. And just kind of explaining it took me 40 minutes to work out. So hopefully somewhere along this explanation, you learned a little bit here. All right. So with that in mind, let's do the second half of the exam. And that was these free response. And you'll see that these are a lot like the multiple choice with a lot more detail. And pretty generous on the partial credit. And so I want to see your thinking here. And of course, this is 60% of the exam. So this is most of the exam here. And so you can kind of see this first one has that projectile motion we were talking about, but it's angled. And so it's harder than that ball rolling off the roof one. And then this one also, there's some frictional force, kind of like that skier we just did, but perhaps even harder because we're kind of, everything's tilted at an vertical, and so we got to think about that one. And then this one, one object and another object, so maybe a part of this hard one is it got two objects to keep track of. Now, one of them has no air resistance, so that's pretty straightforward, but the other one does. It has a non-constant acceleration, so we got to do some calculus here. And so all of these have their, challenges, if you will. So hopefully you were able to do two of these three decently here. So let's try this one. Here we have a firefighter shoots a stream of water from the top of a ladder. And so I don't know if drawing a picture helps here, but here's my firefighter shoots this stream of water. It's coming off at some initial velocity, and the angle is 16.5. It says the nozzle is 22, and so some distance up here, 22.1 meters above the ground. The water leaves the hose at an upward angle of 16.5 degrees. The water then enters a window that is 9.75 meters above the ground. And so maybe over here is our building. And our building has a window here. So the water shoots up and goes into our window. And the window is lower than the firefighter. Above the ground. Now, the horizontal distance between the nozzle and the window, so going across in this direction, is the 27.8 meters. And then the question is, what is the speed of the water? And so, as you heard me say in the multiple choice, and I did a couple times here for our motion, is separate this into x and y. And so apply your equation for the x motion here and the y motion here. And so maybe I'll do this x equals x initial plus initial velocity in the x times time plus 1/2 acceleration in the x t squared. And maybe at the same moment I will think about the same equation in the y direction and see where this gets me. So we've got a bunch of distances involved, and that's why I kind of like this one. But I also know from past experience that vertical motion usually kind of helps me with time, and I can put it over to here. And so I think I can probably do something like that. Let's see here. If I say that maybe over here is the origin, I'm going to say then the water lands at 27.8 meters away and started at a position of 0. When it comes to the initial velocity in the x direction, I guess that would be the total times this cosine of 16.5. And then there's no acceleration in the x direction. And so this right here gives me something to work with. Getting rid of the zeros, I have two unknowns, the initial velocity and the time. Okay. Hopefully then I'll have the same two unknowns over here, and so that I can put them together and have two equations and two unknowns. So let's see, we're gonna land at a final position of 9.75, and we're gonna start at 22.1. The initial velocity would be v naught, and then this would be the sine of 16.5. And the acceleration in the y direction would be that negative 9.8. And if it'll be okay with you, I'll bring the negative out to the front of it. And I'll even put the 1/2 together so that I get something that looks like this. And in fact, maybe I'll move this to the other side. And so I get the 9.75 minus the 22.1. And this would then say negative 12.35 equals initial velocity sine of 16.5 t minus 4.9 t squared. Perfect. Because notice that this equation has the same two unknowns. So I can solve for one variable here and put it into here. And by the way, notice that this, when I put the two heights together, the final and initial, that would be final minus initial. That's the change in height. I get a negative 12.35. So yeah, that makes sense. The water went down. The total effect here is that the water went down 12 meters. Okay. Now, I'm looking for initial velocity, because I could do this either way. And this one, I could easily solve for either initial velocity and time and then put it into here. And of course, whichever one I solve for will be eliminated when I substitute it in. So I'm kind of thinking the way to go on this one would be to solve this for time. Because then when I put it into here, time is gone, and the only thing left is initial velocity, and so I can go through some math and get initial velocity. So why don't I do that? So this would be the 27.8. And when I bring this over, there would be an initial velocity, and there would also be a cosine of 16.5. Now, at some point, I know that I'm going to put in the value of 16, or cosine of 16.5. And so I'm kind of thinking maybe right now might be the time to do that, because then I can combine it with that one, and I don't have so many terms to write. So I think I'll do that. So why don't I take the 27.8 here and divide it by the cosine of 16.5, and this gives me a 28.99 over the initial velocity. And I'm going to put that now into this equation. So just copying down the negative 1235, and then right here in place of time, put 28.99 over initial velocity. And then, of course, I also have minus 4.9. And then putting in my time here would be this 28.99 over initial velocity. And this is really nice right here, because initial velocity cancels out, and I just got a number right there. This would be what I have, the 28.99 in my calculator, multiplied by the sine of 16.5. And so this is an 8.23. guess that gives me then a little more space over here. That's nice. 28.99 over initial velocity. Of course, then notice that this number can be moved and combined there, and so it would become a negative. So I guess I would have a negative 12.35. And then as I bring it over, I'll subtract that last answer. And so this here is a negative 20.58. And this is also a negative. And that's good. The two negatives are going to cancel off. But let me do a little math here. Because when you square something, that means square the numerator and square the denominator. So I'll do denominator squared first. In the numerator, I'll do this 28.99 and square it. And then let me not forget to do the 4.9. And so this is a 4,118. And then, of course, like I said earlier, the two negatives would cancel off. And I can bring this over and get the 20.58 V naught squared equals the 4,118. And then I can bring this over by division. So let me take this 4,118 and divide it by the 20.58? Yeah, 58. So that would be velocity squared. Let me take the square root of that finally. And 14.1 meters per second is my answer for number 1. All right. So kind of a tough one here. I agree. That it's going to do the two-dimensional motion. And, of course, hopefully lots of partial credit if you didn't get the whole thing right here. And hopefully just something real simple. Believe it or not, it could be as simple as just having your calculator in radians mode. But it could also be, using a wrong sign or doing some math wrong. So those aren't too problematic mistakes. But looking a lot here for logic. So, like I said, I want to see your thinking process. And usually I found that even though students maybe not get the exact answer, they usually have a good gist. They've got the two motions. One goes into the other. They just do something real silly like a sine or a radian mode. Or maybe something more significant like they kind of mix up X and Y, or maybe they mix up sines and cosines, But again, still not the end of the world. Looking for logic there. All right, well, let's try number 2 here. And so number 2 has a diagram for us, so maybe I'll kind of use this diagram. Well, there's 2 parts to it, so maybe I better make my own diagram here. So maybe I'll say let's just kind of focus on A here for the first part. But they give us the mass of the block, and so if this is the free body diagram, I'm just going to put 14.4 kilograms here for its mass, and it's held stationary against a vertical wall with a push of P, and so there's the P, and it's angled at 65.2 from the horizontal. So starting with a free body diagram here, I would say that what I have is gravity, and the phrase I've liked to use is gravity and everything touching it. So what's touching it would be this push, whatever this is coming from. I kind of imagine, somebody with their hand pushing on it. And so they're giving a push. So this hand is angling up. And I don't know if you want to draw the force down here, where kind of it shows in the picture, or over here after But of course, it means the same thing. And I'll change maybe a color here because that push, P, is really saying it is a little bit in the x direction plus a little bit in the y direction. You might call this px and py. Those are our components. So that's what the push is doing. The push has both a horizontal component and a vertical component. Now, also touching it is the wall. And the wall then would be pushing perpendicular. That's the normal force. And probably the thing that might be a little challenging here is to say, well, wait, what direction is that normal force? Because we did a lot of problems where the table was, horizontal. And so the normal force was up. The normal force was always perpendicular. We also did problems on an incline. And again, the normal force was always perpendicular. This one went to the extreme, if you will, and had a vertical wall. And so the normal force would be horizontal. Now, also, the wall could produce some friction. And I say could because in part A, it says, what is the magnitude of the push if the wall is frictionless? Whereas B then includes some friction. And so B is going to be a little bit harder, but I guess I'm done with the free body diagram then for A, because I just have gravity pulling down and everything touching it. And there's just two things touching it, the hand and the wall. And again, as you have heard me say many times, very nice to take your paper and just kind of cut it in half and deal with stuff on the X direction and deal with stuff in the Y direction. Okay. Now, in the last problem, this was motion X and Y. But here, this is going to be forces X and Y. So I'm going to say add up all the forces in the X direction, set it equal to mass times acceleration in the X direction. And here I'm going to say add up all the forces in the Y direction and set it equal to mass times acceleration in the Y direction. Okay. Now, one thing that is easy, if there's anything easy about this problem, is they say you're just holding it up against the wall. So we know the acceleration for both left and right is 0 and up and down is 0. So that makes our math a little bit easier because we have a 0. And so this says add up our forces in the X direction and set it equal to 0. Whereas this one says add up the forces in the Y direction and set it equal to 0. All right, so looking at our free body diagram, if I look at the X direction, I'd say gravity is straight down, so that's only Y. So maybe I'll put that right here. So this is minus mg. The normal force is only X, and it's negative, so I'll put negative normal force. The one that is a little harder to work with is the push because it is at an angle, and so it has what we call components. It has a little bit horizontal and a little bit vertical. And let's start with the horizontal. First of all, the horizontal will go in the column for X, and it will be to the right, so it'll be a plus. And it would be this angle and then adjacent to it. And so these are vertical angles. They're the same. This is the 65.2 they talked about. So the X component must be P times cosine of 65.2. Whereas the Y component, so going into this column, would be upward, so there's a plus. And the Y component is, opposite of this 65-degree angle. So it would be sine. So that would be P sine of 65.2. Okay. Now, another reason A is a little easier than B is that once I write these out, you can see that there's only one unknown here, which is P, which is what they're asking for. So I could solve this for P. Now, technically, once I solve for P, I could come back over here and then solve for the normal force. But that would just kind of be a waste of time because they're not asking for the normal force. And I don't need it, at least for A. It's going to change in part B, but in A, I don't need it. So let me kind of put this in. Let me leave the P sine of 65.2 alone and move the mg to the other side. Let me now divide by the sine of 65.2, and that should give me the answer to part A, the push. Okay, where'd my calculator go? All right, so I'll do the, what is this, 14.4 times 9.8. So there's the weight of it, 141. By the way, it kind of makes sense then, as you'll see, when I divide, I'm going to be dividing by something less than 1, and so the push is greater than the weight of it. And that makes sense because we're trying to hold it up here, and we are only using a component of our push to hold up the weight. So this y component needs to be the 141. And that means our push has to be greater than that because this push is made up of a horizontal piece and a vertical piece. All right, so finishing the math, I can then divide by the sine of 65.2, and I get 155, and I'll leave it at that, newtons, and so there is the push. Okay, now for part B, things get a little more complicated because it says, now if the coefficient of static friction is 0.5, so there's quite a bit of friction here between the wall and the block, what is the minimum amount of push needed to hold the block? And notice it needs to say minimum because we have this idea that the static friction can be less than or equal to the coefficient times the normal. And I don't know why I used a capital N. I'll use a lowercase n. That's what I did in part A. But maybe I did that because I think your book does a lot of capital N's. Okay. But that then is an inequality, and the minimum would occur when I'm using the most friction to help me hold up the weight. So what I'm going to do is say, okay, the static friction is going to be equal to the coefficient times the normal. And that's the kind of the key in that phrase. But maybe I better begin this one, like all of them, and say, once you get a good physical picture, the next important step is to do that free body diagram. And so, as I was saying the last time, and we'll repeat here, do the weight of it, then do everything touching it. So there's the P from, somebody's hand pushing up. And then the wall, and then this time the wall is going to be pushing back with a normal force, but also some friction. And friction is opposite of the way it wants to slide. So if you're just holding this up with a minimum effort, you're going, okay, hold it up. You are actually saying the friction is in an upward direction. So in other words, you're kind of using the friction of the wall to help support it. That's why in part B, won't surprise me that if we get a number less than the amount of push we needed. Last time, we got 155 is how much push we needed without any friction. But now friction's actually helping us hold it up. And so I suspect that this P is going to be less than 155. And it is a pretty good, significant amount of friction. So it wouldn't surprise me if it is a lot less than 155. Of course, how much friction depends on this normal force. So, and that depends upon, when we break this down into its component, how much is being pushed into the wall, because this has to push back. And so I'll just set up a free body diagram like I did in A, and I will kind of do the same thinking that I did in A, where I'm going to say, let's add up all the forces in the x direction, set that equal to mass times acceleration in the x direction. But for this case, that acceleration is 0. And then likewise here, I'll do all the forces in the y direction, mass times acceleration in the y direction. And then the easier part of this problem is that the acceleration would be 0 for them. So I can just set this equal to 0, and then over here, I'll set that equal to 0. And so hopefully this looks a lot like A. I'll just go to all my forces. The difference, though, is I will have an additional frictional force. And so if I start with the mg, that one goes in the y column. It's all vertical. It's all down. If I go to the normal force, that's in the x direction, and it's negative, and that's all x and no y. If I do this new one, this frictional force, it is plus force of friction, static friction, and it's upward, and it's all y, no x. And then the harder one is these components again. And so again, recognizing that this is that 65-degree angle, 65.2, I would get right here a P cosine of 65.2. So notice this equation is the same as we did in A, because we didn't have, when we added the friction for part B, we added only to the y components of it and not the x. So this is that same equation. Now, the y component of P was also in an upward direction, and so I'll put a plus. It's like I put a plus here because the horizontal component was to the right, but then this has the sine of the 65.2. And so let me grab that equation from part A. You can see that the only thing that changed was we have now this added frictional force, and it's in the upward y direction. And so that's the difference. Okay. But that does make the math a little bit harder here, because if I do as I said right here and replace the static friction with its maximum, this right here becomes mu times the normal. And if it'll also be okay with you at the same time, I'll take the negative mg and move it to the other side. And so this one is going to require us to get the normal force over here in this column. And if you remember in part A, we didn't have to do that. In part A, we only had the unknown P, and we can work it out. But now we have the same two unknowns. We have the P and the N. The normal force is unknown, so we've got to solve a set of coupled equations. So let me come over here and solve this for N. So I'm going to bring the N to the other side, and this becomes P cosine of 65.2. And I will use that over here. So this will be my coefficient of friction, and then the normal force is P cosine 65.2. And then this is P sine 65.2 equals mg. And now I've eliminated n. That's the whole idea of a system of equations. You take one equation and solve it for an unknown, and you plug it into the other one, and so that one you solved over here for the first time goes away once you plug it in, and you end up with just the other variables, which in this case is the p. And again, the math is a little harder because there's a p in each of them, so I'm going to have to factor out the p. And now, to solve for p, I can divide by all of this. And put it into my calculator. By the way, be careful. Notice how the normal force depends on how much you're pushing it. And you might be tempted to say, oh, well, how hard I'm pushing, and go back to A and say, well, I'm pushing with P. But you're not going to be pushing with the same amount as A. And so you might be tempted to put in the value that you got in part A right here to get the normal force to put in here to solve for P. But that's kind of a circular reasoning. You're saying, I know P here to get the normal force, and I'm going to use that here to find P. And then you get a different value of P here than you used over there. And that is, right, contradictory. So that obviously is not a good option. All right, so quite a few steps here. But let's see how this works out here. So why don't I do this denominator, because the mu is the 0.15, so then I will multiply it by the cosine of 65.2. Then I will add it to the sine of 65.2. And so that's the denominator. Now, the numerator is the same as before. I'll just recalculate it, but I think that's the weight, 141, yeah. And so if I divide it by, and I'll just go up and do a copy and paste that denominator, I will get a push of about 126 newtons. And so sure enough, less than the 155 we got in A. Okay. All right. And that's a good one also. Let's move on to number 3. All right. So number 3, this is the one that's saying that it can be a little tricky. We got to keep track of 2 objects. So maybe I'm going to do kind of the same thing. I'm going to draw a dividing line, and I'll look at the heavy object first and then the lighter object, but they drop from the top of a cliff. And the heavier one, the rock, is much easier because the air resistance can be ignored for the heavier rock. But for the lighter one, the acceleration does change according to this formula. Okay. How far apart are the two after this much time? So let's just find out how far they fall after that time and then subtract the 2. That'll be my strategy. All right, so let's look at the heavy rock. And the heavy rock says, okay, you could take the initial velocity and the acceleration, And if you punch things in and say, okay, well, we are going to start at 0 height, and we'll start with 0 speed, calling down positive, that's okay, because everything goes down. I'll just call it a 9.8, and the time is 2.75 seconds. We can get the position of the falling rock. So 1/2 times 9.8 times 2.75 squared. And so we're looking at about a 35.05 meters for the dropping of the rock. Now, the harder part of this problem is definitely the other object, because they tell us the acceleration is a function that is changing with time, which obviously is kind of connected to how fast it's going. But what you don't want to do is use this equation. This was our discussion about our 5 kinematics equation. This was number 2, and it's very useful, but it only applies when you have a constant acceleration. And so you can't use it. Plus, you don't even know what the number is, although I suppose you might be tempted to do something like this. You might be tempted to find the acceleration when time is 2.75. And if you did that, then you would be finding the acceleration after it has fallen quite a bit. And then you might want to put it into here, but if you did that, you would really be messing yourself up, because that would, not be the acceleration for all those moments in time. In fact, you might even be tempted to do something kind of silly like this. In fact, I could see the temptation here is to think of this as some kind of formula where you just are plugging and chugging in here, not really understanding where it came from. You might do something and say, okay, we would get a 1/2, and in place of A, I could just put the formula. And I wish it was that easy, but that's not where that came from. Part of coming up with this equation was recognizing that this had to be treated as a constant. So you can't later on say, oh, it's not a constant, it's a function, and put a function in there. I wish I could. That would make it a little easier. And as you'll see, you don't get the same here. So what do you do? Well, this is where our calculus came in. We could say you can get velocity if you integrated acceleration. So let me integrate this function. And you could think of this as time to the 0 power, because when we do an integral with power, we add 1 to the exponent and divide by that new exponent. So in this case, t raised to a power of 1 would mean we add 1 to the exponent and divide. So this would be our equation for velocity. Now, we're not quite where we need to be. We need to take the next step, which is position. And position was that same thing that we can integrate it. So finally, we will get an equation for position. So I'll take the 9.8, and right now I have t to the 1, so I would add 1 to the exponent and divide by the new exponent. And here I have a t squared, so I will add 1 to the exponent and divide by the new exponent. And then this is my equation for position. So let's use it. And by the way, had we done this mistake of putting a as a function, we would get something kind of close to this. but these numbers out in front would be a little different. The powers would work out right because of the type of function we have, but in general, it doesn't work. All right, so now let's get the position of this plastic ball. So I'm going to take the 9.8 and multiply by the time, 2.75 squared, and divide by 2. Then I will subtract the 1.2 times the time, 2.75 raised to a power of 3. Divide by, and okay, if I do that in my head, 2 times 3, that's a 6. So divide by 6. So this should come out to be 32.90. So it kind of makes sense then that the falling rock is further down than the falling plastic ball. Plastic ball had an acceleration that started at 9.8, but then as time went on, it got less and less of an acceleration, and therefore ended up with lower and lower speed compared to the rock, and therefore lower and lower distances compared to the rock. So what you might call the delta, how much further is the rock compared to the plastic ball, would be the 37.05 minus the 32.90, and we're looking at about a 4.15 meter difference between the two. All right. Well, hopefully you got a lot of that partial credit in there and things like comparing one to the other. Even if you punched in that function, there's going to be a lot of partial credit there. So I'll have to think this through and start grading them, but there's the exam. All right. Hope this helped for any of the questions you had. Take care.